Hi, this video briefly introduces our paper Redundancy Resolution as Action Bias in Policy Search for Robotic Manipulation and presents the results visually in simulation and on the real robot. A detailed insight into our method and the results is given in the paper. Our work was presented on the Conference on Robot Learning in 2021. When doing policy search for robotic manipulation, for instance, when using reinforcement learning or evolution strategies, it is often not enough to only specify the main objective in the reward. We usually need to describe secondary objectives as well. For instance, in a reaching task, we are not only interested in reaching the target, which would be the main objective, but we also might want to keep distance to obstacles. Or we might want to stay close to a reference configuration in order to avoid very skewed configurations. The necessity of secondary objectives becomes more important for robots with higher degrees of freedom. However, embedding secondary objectives into the reward as well is a hard thing to do. It often requires expert knowledge and a lot of fine-tuning. Further, found rewards for secondary objectives need to be readjusted or reweighted when using a different algorithm or applying the same algorithm to new tasks with different main objectives. This is because the main and secondary objective are optimized in the same action space, which intrinsically causes interference during optimization and calls for prioritization of different objectives in the same reward function. Our idea is to optimize secondary objectives separately in a subspace of the actual action space. This subspace of actions is redundant with respect to the main objective. This is a well-known approach from conventional control, where it is considered as redundancy resolution, which is a null space optimization technique. This allows us to keep the reward function as simple as possible, which streamlines the algorithm setup. We show that our approach requires little to no fine-tuning, even when applying to different policy search methods and across different tasks. We start by defining the action space and the redundancy constraint. The action space consists of desired joint velocities q.d as well as a binary value kappa d telling whether the gripper should open or close. Accordingly, our policy takes a state st as an input and outputs an action at. The redundancy constraint is defined in the sense that we consider two actions redundant if the reward of both actions is equal. That is, in a state st, an unbiased action has the same reward as an action biased by bt, where bt only consists of desired joint velocities. We consider this type of redundancy as task redundancy. Our reward function is mainly based on the end effector position. That is, a robot is considered redundant if it has more joints n than the Cartesian space's translational degree of freedom, m equals 3. In this case, our task redundancy definition equals the kinematic redundancy definition. This allows us to derive the bias bt using redundancy resolution. Hence, we search for the bias q.0 in the null space of the Jacobian JV. The expression in the brackets maps an arbitrary vector g into the null space of JV, where JV superscript plus is the pseudo-inverse of JV. Now we can use the vector g to consider secondary objectives. For instance, we can define losses we might want to minimize, such as for pushing the robot towards a reference configuration or to maximize the distance between the surrounding obstacles and the robot links. Then, at each step t, we go one step alpha into the direction of the negative gradient of L. The resulting bias is added at each step t to the actions taken by our parameterized policy pi. To demonstrate the applicability to different policy search methods, we have tested our approach with DD3. An actor-critic reinforcement learning method, as well as OpenAI's evolution strategy. Let's take a look at the effects of redundancy resolution, that is, only q.0. Here, we would like to minimize the distance between an initial skewed configuration and a reference configuration. You can observe that q.0 does not have any effect on the end effector position. As can be seen, we can use a reference configuration to push the robot towards a more upright configuration. Here's the influence of redundancy resolution when maximizing the distance between the robot links and an obstacle, here the cube. Okay, let's take a look at the training results. Here, TD3 with and without redundancy resolution with respect to a reference position on a reaching task. After 36,000 episodes, both agents have successfully learned the task. However, the one without redundancy resolution has a significantly more skewed gripper position. We can directly transfer the learned policy to the real robot. As can be seen, the agent without redundancy resolution has a lot of self-motion, especially at the target point. Both agents can generalize to a new starting position, however this increases the self-motion of the one without redundancy resolution. Now let's take a look at the training results of an evolution strategy, here the one from OpenAI. At this point, the agent without redundancy resolution has learned a backflip behavior. It is expected that this is because at the beginning of training, the agent focuses on approaching the spawn boundary of the target. After learning how to approach the spawn boundary, the agent then focuses on the single target, which causes this backflipping behavior. The evolution strategy with redundancy resolution did not learn a backflipping behavior and an overall more upright position of the gripper. Now let's take a look at the results of the evolution strategy on the real robot. Here, I've slowed down the policy to around 20%, as the final policy is very likely to get contact with the table. As seen here and before in the training, the agents did learn to approach the target, yet did not learn to stay at it, unlike the agents of TD3. Moreover, on the agent without redundancy resolution, the backflipping effect reduces when slowing down the policy. Now let's take a look at the results of a TD3 agent on a pick and lift task. At the end of training, both agents are able to grasp at a success rate of around 90%. However, the gripper orientation is now particularly important, as a skewed gripper position might cause contact with the table. Let me show an example on the real robot. Note that the gray foam plate is added to compensate the height of the additional plate under the robot. You can see here the influence of redundancy resolution. The agent on the right side has a much more upright gripper orientation, which is less likely to cause contact with the table. Moving the object closer to the robot shows that not handling redundancy might cause contact with the table. Note that we do not necessarily need to pass an upright reference configuration. We can pass any reference configuration we want. So let's pass a reference configuration which is tilted to the right and see what happens on the pick and lift task. Note that the bias is not a hard constraint. As you can see here, the agent can learn to overcome the bias and grasp straightly, as before. Let's compare a skewed and an upright reference configuration on the real robot. As mentioned before, we can use redundancy resolution for collision avoidance as well. So let's take a look at the results in a reaching task. Note that we have defined the redundancy in the sense that the gripper position is not influenced. This is why collisions might occur if the agent has learned a trajectory that goes through the obstacle. Let's take a look at the results for collision avoidance on the rear robot. As can be seen, the robot ducks under the obstacle without touching it. It is noted that the agent cannot see the obstacle. Only the bias is pushing the robot links away from the obstacle. Here's what happens when we do not use redundancy resolution for collision avoidance. Thanks for watching.